Okay, it's time to have a little chat now about rates of change and kinematics. Now you might, okay, I say, what's the deal here? Because rates of change, we've been talking about that for a while, and that's true, we have, and this whole differentiation business is about rates of change. And kinematics, we've looked at before. This is motion in a straight line, motion of a particle or a body in a straight line. All right, so that's we're going to just have a little closer look at that now that we've done some work on differentiation. And rates of change, well, let's just do an example here, and I'll show you how differentiation is going to help us with a rate of change now that we've got some differentiation rules up our sleeve. So, okay, so here's an example, and it's out of your textbook. A balloon develops a very small leak and decreases in volume. Its volume, v centimeters cubed at time, t seconds, is given by this equation here, where t is greater than 0, t in terms of time. So this is our volume. So if we put in t, we find out what the volume is. You get it. It's decreasing. As t gets larger, this volume will decrease. So we might look at what's the rate of change of volume. Well, what's the rate of change of volume? Now the volume initially, we put t equals 0 in here, you get 600. So it's 600 centimeters cubed initially, and it reduces. And after 10 seconds, we could put 10 in here, and it would be 10 squared, that'd be 1, that'd be 10 times 10, that's 100, so 600 minus 100 minus 1, which would be 499 centimeters cubed, but it's not asking for what is the volume after 10 seconds, it's asking what's the rate of change of the volume after 10 seconds. So a rate of change of volume with respect to time, this here, that is dv dt. Right, that's the derivative of v with respect to t. Now this is a direct application of what we've been doing with curves. We've been looking at dy dx, haven't we? Change in y with respect to x. That's when we've got y and x here, and we've got a curve, and it's y equals, x squared or whatever. Dy dx is the rate of change of y with respect to x. Here's the same deal, except now we've got a v here, and we've got a t here, and we want to know what's happening with v with respect to t. What's the rate of change? How quickly is it changing? At various points. So we derive this function. So dv dt is, well, let's have a look here. We get minus 10, that 600 goes to 0, we get minus 10, the 2 comes down, so it's minus 2 over 100 or minus 1 over 50, and the t squared becomes t. So it's minus 10 minus 1 over 50t. That's the rate of change. So that will deliver for us the rate of change at any point t. So after 10 seconds, so therefore, when t equals 10, the rate of change of volume is equal to minus 10 minus, put 10 in here, that's 10 over 50, or 1/5. So it's equal to minus 10 minus 1/5, or minus 10 and 1/5 centimeters cubed per second. And that's the rate of change after 10 seconds. After 20 seconds, so we could do part 2. That's part 1. Part 2, when t equals 20, the rate of change of volume with respect to time is equal to minus 10 minus 20, 2/5, which is equal to minus 10 and 2/5 centimeters cubed per second. Okay, now we turn our attention to the final part, which says, so part B, for how long could the model be valid? B, for how long could the model be valid? So this is saying, right, so how long is this going to be valid for? Well, as soon as the volume slips beneath 0, it's not valid anymore. So we're going to find out at what point volume goes to 0. So we need to go back up to here and find out when v equals 0. So solve this quadratic equal to 0. And it's probably easier to graph it, which I'll do now. Okay, so here's the graph on the screen. I've just taken a snapshot of it. This is a massive concave down parabola, but you can see what's going on here for the bits that are relevant for us from t equals 0, excuse me, when it goes through 600. This is the point here we're interested in, when volume dips below the 0 on the, or dips below the t-axis. therefore becomes a negative volume. That makes no sense, and I've found that point of intersection there with the x-axis is 56.8. So we need to go back in to, and that would be at t is equal to, or for how long could the model be valid? You would say therefore that it's valid between t being 0 and 56.8. That would make sense. Okay, moving on to some kinematics examples. And kinematics deals with the motion of a particle in a straight line. So what we're going to do here is just have a look at an example. Actually, let's get down some basics. So displacement. So if just to recap here, displacement, which is s, is the position of the particle. Position of it, displacement from the origin. Velocity. Now velocity is going to be v, which is going to be velocity will be equal to the rate of change of s with respect to time. So that's the velocity of the particle, and the acceleration, which is a, will be found by the rate of change of velocity with respect to time. So what we end up doing is working with a displacement equation, or if we've got a displacement equation, deriving it to get the velocity, deriving again to get the acceleration. So let's have a look at an example. Just going to pull one from the book. Let's say example. All right, so I'll write this up. Okay, so we'll look at this example here, which is again out of the textbook. It's a point moves along a straight line so that its distance x centimeters from a point O at time t seconds is given by this formula here. Okay, so let's investigate. Let's investigate the initial situation. So the word initial situation is when time equals 0. So let's have a look at okay, when time equals 0. What we should do is firstly work out what our velocity is. So our velocity, which will be dx to t in this case, x representing the distance from a point, so x is the displacement, which is 3t squared minus 12t plus 9. Okay, that's our velocity, and our acceleration is going to be the derivative of the velocity with respect to time, so that will be 6t minus 12. Okay, so there's our velocity and acceleration and displacement equations. So the initial situation, when t equals 0, right, when t equals 0, our point is at 0, our velocity is 9, and our acceleration is minus 12. So what that means is initially, so let's start to build a picture of what goes on here. We've got well, I'll just pop this down here, along this line here. So initially, if we put time equals 0 here, then the point starts here on this line at 0. So that's x equals 0. Now its velocity is 9, so it's heading off in the positive direction, so it's going this way. And acceleration though is negative 12, so it'll head off in this direction, but there's a force initially that is pulling it back. So it will be starting off to the right, but it will be slowing down. So when t equals 0. So what we should do is then find out, well, let's just see after 1 second, just to see what's going on. So when t equals 1, our displacement is 1 minus 6 and minus 5 plus 9, so it's at 4 when t equals 1. So we'll pop that down here. When t equals 1, the point has moved up here to x equals 4. So x equals 4, our velocity is equal to, at 1, 3 minus 12, so that's minus 9 plus 9, so that's 0. So it's stopped, interestingly. and our acceleration at 1 is -6. So it's moved here in the first second, but it's now stopped, and because the acceleration is negative, so you can see the acceleration has slowed it down to the point where now the velocity is 0, it's going to turn around and head back this way. So what we need to do is probably work out when the velocity is 0. So when is velocity 0? And we can work that out by solving our equation here, our velocity equation, 3t squared minus 12t plus 9. Solving that equal to 0. 3t squared minus 12t plus 9 equals 0. Divide through by 3. T squared minus 4t plus 3 is equal to 0. And factorise this, so it's t minus 3, t minus 1 is equal to 0. So t is equal to 1, 3. So after 1 second, the velocity is 0, and then again after 3 seconds, the velocity is 0. We've already seen what happened after 1 second. Let's find out at t equals 3 what's going on. So at t equal to 3, velocity is equal to 0, but where's x? X is equal to, put it back into the equation so you can see what's going on here. We're just examining the movement of this particle. And what the effects, the velocity and acceleration are at various points. So at t equals 3, we've got 27 minus, what's that, 3 squared is 9, so minus 54 plus 27. So we're back to 0, aren't we? Let's check that again. 27 minus 54 is minus 27, so we're back to 0. So at t equals 3, v equals 0, x is equal to 0. What's the acceleration equal to? When t equals 3, that's 6. So now there's a force on it, so it's back here at t equals 3. So what it's done in that first few seconds is it's gone this way, turned around, it's come back here, and that's 3 seconds. And now velocity is 0 again, so because the acceleration is positive, it's going to turn around again and head off in this direction. And I would suggest that because it doesn't turn around, because velocity is never 0 again, it goes on forever in that direction. So let's say, after at t, when is acceleration equal to 0? That's an interesting one. Acceleration is equal to 0 at t equals 2. So when is acceleration equal to 0? And what does this mean? So when the velocity is 0, that's obviously when it stops. There's no velocity. Then acceleration, the force of acceleration takes over the direction it goes in next. But when is acceleration 0, and what does that mean? Acceleration 0 is when at t equals 2, and that means we'll have maximum velocity. So that's at t equal to 2. And what does it mean? When is acceleration at t equals 2? What does this mean? What does this mean? It means maximum velocity. So when we put t equals 2 in there, we get v equals, into the velocity equation, 2 squared is 4, 3 fours are 12, minus 24 is minus 12, plus 9 is minus 3. So maximum velocity is minus 3, and we're doing this in centimeters per second. So that's as fast as it gets. So after 2 seconds, it's heading back this way. It picks up top speed because acceleration is 0. Then it slows down again to another velocity of 0 again. Acceleration is positive, it takes off. So if we looked at, let's just say now at t equals 10, for instance, then what's x equal to? It's 1,000 minus 600, which is 400, plus 90, so at 490. X equals 490, so you can see it just shoots off now after 10 seconds really quickly in that direction. And I would suggest the velocity is also quite strong at this point. Velocity at t equals 10, 10 squared, 300, minus 120 is 189. So it's going at 189 and getting quicker centimeters per second. And our acceleration is equal to, at 10, 60 minus 12, 48. So as you can also see there, 48 centimeters per second squared. You can see that as now time increases, acceleration increases velocity, and this thing just burns off into the right forever and ever. Okay, that's enough for me. Hopefully that's a good intro for you to tackle the work requirements from exercise 20B. I'll see you on Thursday.